Thanks. All right. So, see, last time I said that the chi-square convergence. So all chi-square tables, there's this asymptotic convergence of the chi-square statistic to a chi-square distribution, but they're non-uniform. So if they're non-uniform, you might ask me, do I trust the p-values? Right? They don't converge at the same rate. But what I want is really an unbiasedness. I want it such that if a tree splits on a certain variable, it is because there is a lot of signal in that variable. It's not because it's just by chance or because we overfit the data by searching too hard, right? So how would you verify that any algorithm has this unbiasedness property? That's very easy, actually. So what you do is you give me a data set and you give me an algorithm. And I want to check whether the algorithm has unbiased variable selection. Unbiased variable selection means that if the X variables are independent of the Y here is the type of drive, four-wheel drive, front-wheel drive, and so on. If Y is independent of the X's may be related, dependent. But if the Y's are independent of the X's, then the chance that X1 is chosen to split the root node, or X2 and so forth, they are equal because Y is independent of the X's, right? That's unbiasedness. So you can easily check whether any given algorithm or software has this unbiasedness property. Just do a simulation. Take a data set, randomly permute the Y so that you destroy the relationships between X and Y, and see which variable is selected. Then do it again, randomly shuffle Y and see which variable is selected, right? And do it 10,000 times, 100,000 times. And at the end, find out how often is X1 selected, how often is X2 selected, and so forth, right? If they're all the same, then the method is unbiased, right? If a method has some peculiarities that it likes to, like cat, that would like to select on variables that it can find more apparent splits, then you'll find that those variables, like make here for the cat method, make will be selected very often, even if Y is independent of X, because there's an exponential number of ways to split on make, right? So after I came up with this chi-square thing, I found that when I do the same simulation myself, the probabilities are not all equal. That's because of the non-uniform convergence of the chi-square test, right? So they're about equal, but they're not as equal as you want. So what did I do? I did exactly what you would do to check out my method for it, whether it's unbiased or not. So internally, Guide would compute these tables, but it would not stop that. It will now do these permutations or this randomization of the Y's many, many times to find out what is the chi-square value. So say the Wilson-Hilferty converged chi-square value. All right. And it will find that some of them actually on average is a little bit higher, some on average a bit lower. What do I do then? I just divide my real, the first one that I get, divide by this average. That is a simulated mean of these chi-squares. So that on average, if the Y's are really independent of the X's, then I should, in theory, get them exactly right. So this is a second order correction. The first order is the asymptotic chi-square, right? But because the asymptotics are non-uniform, I do a self-calibration, right? So suppose H category, for example, the chance that is selected is a little bit less than other variables. That means its chi-square value tends to be a bit lower, maybe because it only has 4 or 5 categories, right? When I do the simulation, the average will also be similarly a little bit lower. Then I just divide by the mean of that simulated thing to sort of boost it up. Okay, so it's a kind of bias correction by scaling. So then this makes it basically foolproof. Okay, so you cannot take guide and show that it's biased by doing this random permutation, because guide itself does the permutation to adjust for that. Okay. So I think this is very important because all these methods give you a tree. You like to trust the tree, just like when you go to a doctor. The doctor says you have this disease. You would like to trust the doctor, right? The moment you know that this doctor cannot be trusted, you will not see the doctor anymore. So the moment you know that a certain algorithm is biased, why would you use that algorithm for interpretation? The algorithm may be good for prediction accuracy, right? But if you want to try to interpret the model by seeing which are the key variables and how do they work, then the moment you know that there is bias, you shouldn't put all the faith in the solution. Okay, so that's the bias. Okay, now I want to say yes. Yeah, so it depends on what you mean by how you define unbiasedness, right? I define unbiasedness to mean that if y is independent of the x's, then each x should have the same probability of being selected. Right? So if you buy that definition, then I'm just implementing the definition. I don't know how else to define unbiasedness, right?
There's no standard definition.
No. Yeah, unbiasedness to me, maybe it's not the right word. It's really equal probability when there is no relationship, right, between the predictors and the predicted and the dependent variable. So if you permute, then you will actually break up all those relationships, right? You don't want to permute the x's independently because you don't want to destroy the dependence among the x's. So you keep the x columns fixed. You just permute the y column, right? Okay, so now I want to show you another thing that guide does that nobody can do, and I really mean nobody in the world can do at this point. And this is the same data set, but instead of predicting the drive, whether it's four-wheel drive or front-wheel, I predict the type of vehicle. Okay, so the type of vehicle was also a variable which I had used. So let me go back to the car data. Okay, so these are the variables in the car data. The make is the one that is problematic because it has 38 categories. That one causes a lot of pain in computations. I used, I didn't write here, these are the X variables. I predicted a drive in the example so far, all right? Now I'm going to make drive a predicted variable. Instead, I'm going to predict type, the type of car. Right? So I changed the Y variable, right? So in my X data matrix, previously I had a drive column. I made that a Y and all the others X. Now I chose the type, which previously I had used as a predictor, but it didn't seem to be very powerful. Now I use type as my Y to illustrate one point. So type has 6 values. There are 6 types of cars. And so what I'm going to tell you will explain why guide is so powerful in compared to other tree methods in prediction accuracy. Okay, so this is a guide tree, and I try to use a different color for every value of Y. So we have, I think magenta for SUV, purple for pickup, blue for wagon, green for sports car, this is ordinary car, orange for minivan. I think there's 7. 1, 2, 3. There's supposed to be 7. I thought there's 7. Maybe there's just, oh, there's just 6. I think, yeah, there's just 6, right? So there's 6 colors. So at each node, we have this condition. It says now highway MPG, 22.5 miles. If a highway MPG, this is 2004 car, so the highway MPG tend not to be so high. If they are lower, you go to the left. Those with higher mileage, gas mileage, go to the right. Okay. And you see mostly on the left, they're the magenta, they're the SUVs. SUVs are the gas guzzlers. I mean, you do have an SUV here, right? But rarely, you know, at that time, 2004, there are some SUVs that don't consume a lot of gas or petrol, as you say here. But most of the SUVs with low gas mileage, right? And then dealer cost, these dealer costs, how much they cost, right? If they don't cost as much as 4,048, I think it's 48,000, no, probably 4,000, right? Dollars, US dollars, you could have left. No, cannot be 4,000 US dollars. I forgot what the units are. Maybe 48,000. Maybe 48,000 US dollars, right? So the less expensive cars go to the left, more expensive go to the right. Okay. And you notice there's one node that is in gray. I don't know whether you notice it. Okay. So if you run the software, once in a while you'll come up with a node that is gray. All the intermediate nodes, the non-terminal nodes, are always white. Okay, and the terminal nodes will be colored. But once in a while, you will see a node that is gray. In this gray node, unlike say here, this number of cylinders less than or equal to 4 go to the left, otherwise go to the right. For a gray node, you see two variables, length plus width. That's a linear split. Okay, that's a linear split. And so let me clean this up here. Okay, in this split, why is this moving with my pen? Oh. In this split, you see that this left node is predicted to be SUV. This right node is predicted to be pickup. The number beneath it is the number of observations in those two nodes. So 8 observations go to the left, 5 observations go to the right. And then you have two numbers, one number on the side, or each side. Those are number of errors. Okay. So on the left node, there are 8 observations, and the whole node, every car in there is predicted to be an SUV, but there is one misclassification. On the right node, there are only 5 cars, and they're all predicted to be pickup, but there are no errors. That means they're all pickups. Okay. And guide is purposely written so that we split on 2 variables, because then I can show you the data. I can plot what's going on in that node. And that's what's going on. So in that node, there are 13 points. There's a 2 there because that purple triangle is over printed. There are 2 cars there, right? So guide will now use that line, that oblique line. Guide is the only one that will do this. All other methods will try to split vertically, and you find that if you split it vertically, it's very hard to purify them, no matter where you move this vertical line. Or if you split horizontally, right? There is one orange car in there. There's a minivan. Okay, so you find that in this node, the guide uses this linear split. The only error is the minivan. It does a clean job of separating the SUVs from the pickups. And you can see from this picture that given a certain width, given 2 cars with the same width, the pickups tend to be longer. Right? What's the difference between a pickup and an SUV? They look the same, although pickup only has a cab and doesn't have a passenger compartment. Right? But here we don't have that variable to tell you whether it has a passenger a backseat compartment. We just have length and width. But this picture shows that if you have 2 cars, an SUV and a pickup side by side, and they're both as wide, the pickup tends to be longer, right? And so this is a feature that occurs very often on vehicles, occurs on ships, occurs on planes, occurs on animals, fish, different types of fish. They all look like fish, but one species will just be slightly longer and one species will be slightly shorter. Like human beings, right? Asian and Caucasian, right? They all look like human beings, but their proportions, they're slightly different proportions. And you can only catch this with a linear split using 2 variables at a time. So this is very useful if you're trying to apply this in a military situation and you have images of submarines or ships, radar profiles of ships, and you try to identify whether that is an aircraft carrier or whether that's a battleship or cruiser and so forth. In fact, this military application was one of the examples mentioned in the CART book in 1984. They applied it for the US Navy. The US Navy during wartime will take pictures of enemy ships, radar profiles, and they'll store it in a big database. And then they train it so that in times of war, when a Navy fighter goes up and seeks out that ship, right? Before the pilot can see that ship, his radar can see that ship. He cannot see the ship because it's over the horizon, but the radar can get it, and the radar can return the radar profile. So he has to decide what kind of a ship that is. Is it a tanker? Is it a military ship and so forth, right? So of course, CART doesn't have this feature of a linear combination, right? So this is a reason why. So at this point, you see, when you come down to this branch, Guide is having a hard time using axis orthogonal splits because you can't really purify too much. So what Guide does is that Guide will, like this chi-square test, okay? Guide will run through a whole bunch of chi-square tests to look for the best single variable to split. And it will have p-values, like this, right? And you see the p-values here are super small, but they don't remain super small. The moment you go down deep in the tree, the data sample size becomes more and more sparse. Those p-values become non-significant. So what Guide does is that there is a threshold for significance, which is some 0.05 divided by some Bonferroni control of how many variables you have. So once you do not have significance, Guide will flip into this linear split and see if we can get anything out of it. Yes. Yes, I was trying to avoid linear split because if I do a linear split on 16 variables, it's useless, right? You cannot interpret. But this is a split that anybody can interpret, right? I mean, basically, if I can graph it, then I can interpret it. So that's why I could get more accuracy if I don't restrict it to linear splits, right? If I allow, I don't know why this is always moving with me. Maybe I have to touch this. I still haven't learned how to use this. If I use all variables there, then of course I would have a hyperplane in however number of dimensions, and that will do a super job, but I won't be able to see anything, right? So, whereas if I, and that's the reason why we use univariate splits most of the time, because with a split like that, you don't even have to see anything. Just look at the inequality, you sort of know, unless you want to see with the distribution on the highway variable, right? Yeah. So there's always a trade-off. I want the solution, the tree, to be interpretable. I want it to be accurate. Okay. So so I try to squeeze a bit of accuracy out of it by allowing myself linear splits, but I don't want to go overboard and lose interpretability. So I stay on 2 variables, which can be costly because I have to look at all pairs of variables because I don't know whether it's length versus width. It could be length versus highway MPG. It could be length versus city MPG. It could be highway versus city MPG. Right? So I have to look at all pairs, and that can be costly. But because Guide is so super efficient on all other aspects of the algorithm, it can afford this luxury. And that's why other algorithms don't do this. It's not that they don't know. I mean, this is published already. It's in the literature many years. My paper was published a long time ago. They can't implement it. Because if it implements it, you will have to wait days before you get the result, right? It becomes unusable. So that's why, in this kind of algorithms, the internal engine has to be super fast. Okay, you cannot try to do things too perfectly at every point. Then you spend an inordinate amount of time to perfect one step. But then you're doing this recursively, so you cannot afford, and then not only recursively, doing it in cross-validation mode. So after you grow this tree, you do it 10 times again. Or if you want 100-fold cross-validation, it's 100 times more. Okay, so now let's talk about pruning. So yes. Oh, it occurs everywhere. At every point, even in the root node, okay, it will compute this chi-square test of y versus each x. And then it finds the smallest p-value and sees whether it checks smallest p-value is less than 0.05 divided by number of tests. Control for the number of tests. Because if you have 1,000 tests, the p-value just by chance could be smaller and smaller than 10 tests, right? So there is a threshold before this kicks in. Okay. So it's like Louis and I were talking about the Lord of the Rings. In a Lord of the Rings, when they do battle, right, there are certain waves of attack. Maybe they start to shoot arrows, right, to soften the army, the enemy, or maybe they throw fireballs or something. After the archers have done their job, then they send in the cavalry. I don't know whether at some point they send foot soldiers. So this linear split is like that. Okay, I don't want to use it all the time because I cannot show it in this tree diagram. I have to show a separate plot like this, right? Besides, that may cause some problems with unbiasedness. That may be harder to control. So it's like a second level of defense. Okay. Okay. So now, one of the most important criteria, apart from, so unbiasedness is good for interpretation, but for prediction accuracy, you really need to have the right size tree. You don't want the tree to be too short, in which case you lose accuracy. You don't want it to be too big because then you cannot generalize to unseen cases very well, right? So you think that, okay, so we have a tree like that, and we can keep growing it. The tree that I show you here is a pruned tree. It's not the original tree. The original tree will go down, 50 feet below the earth. It goes down until, actually it doesn't go down so much because sample size gets very small already. But if you have a big sample size, it can go very deep. So this idea of pruning is from the CART method, which I think is still the most important contribution of the CART algorithm, is this idea of pruning. Previously, even now, some of the other algorithms that are available, they don't do pruning because pruning is expensive. If you do 10-fold cross-validation to prune, right, then you need to multiply the validation time by 10 times. Some of people use something called pre-pruning, which is like no pruning, which basically they use Bonferroni corrections on this alpha p-values to decide when to stop. But that is not going to be effective all the time because these corrections, nobody really knows what the right corrections are, right? So now, imagine now we have a very big tree, and we know that somewhere along there is a, so let me open up a blank page. Okay, so we have a tree. And it keeps going, right? Every time we cut, so there's a, say here, suppose we cut here, right? Then I have a subtree, right? Without cutting, I have the whole tree, right? So every time I cut, I have a subtree. Every time I have a subtree, I have a model. I have a prediction model. The tree tells me how to predict, okay? So now we do variable selection. Model selection. Now I have a nested sequence of models, and I want to do model selection. I say nested because we're going to cut it and not put it back. Okay, we don't want to be too aggressive and to find the best subtree. Best subtree means after you cut here, now you put this back and find all possible subtrees, right? That is going to be very time consuming. So never go to a barber who would try to cut your hair with the best possible sub haircut. You will never get out of the barber shop. He will cut this and find, oh no, let me put this back and I'll cut that. It will be an endless haircut. So most barbers, in fact, all barbers, do not put your hair back after it's cut. Okay, if you make a mistake here, cut too much, they will just cut a bit more on the left side. So the barber gives you a nested haircut. Okay, the only thing is, when does a barber stop? Okay, if he doesn't stop, you have no hair left in the end. Okay, if it stops too soon, your hair won't be cut very much. So similarly here, we're talking about how to cut this tree. Now, I don't know how barbers do it, but how do we decide to cut a tree? So we have this big tree. How do we decide? Do we go to the lowest branch? So if there's something here, do we cut this first because it's lowest? Do we look at the depth? What happens if there is more than one that's the same depth, right? So somewhere here, maybe there's another one, right? Now, how do we choose? Do we always choose the left? But your left is my right, because you can turn the tree backwards, right? So it's a very difficult problem. And the cut authors solve this in the following way. They think of a bicycle chain. So if you think of a bicycle chain, right? You want to cut this bicycle chain into smaller and smaller pieces, right? What is the normal way of cutting the bicycle chain? You maybe try to stretch it, hang weights and to see which link breaks. That's weakest link cutting, right? So you add hang weights there until they break, and then once you break down, you have two sub chains, and then you break each of them like that, increasing weights. So this is the idea that they use, weakest link cutting. And so how it works is the following. All right. So maybe I can go back to my document, my blank page first. Okay. I need to. No, I don't want to add. Okay. There's a way to add another page, but I think it's faster for me to just erase this. Okay, so what we do is that, like in the lasso, right? You have a loss and plus lambda times complexity, right? So penalized regression, use something like that. Okay, so the idea is the following. They define a cost complexity function. Okay, R of t is the inaccuracy or the total error of the tree based on the same data that you use to grow the tree, because we don't have another data set, right? So whatever subtree we have, we put the same data into it and get an estimate of the error rate. And then we see how complex is that tree. T tilde is the set of subnodes of a tree. T tilde with the absolute values is the number of terminal nodes. T tilde is the set of terminal nodes, and then the absolute value is the number of them, right? So they take the estimated error rate, which is bias, and add some constant alpha, which we don't know, times the complexity of the tree. Okay. If alpha is 0, so we want to find the tree. So if you give me an alpha, I can find the best tree, because I have these subtrees. If you give me an alpha, for every subtree, I can calculate what is R alpha t, right? So every subtree has a value of R alpha t. And if I want to find the minimum value, what the tree that satisfies that, and if you give me the alpha, the only thing is we don't know what is alpha. So just like in the lasso, there's this tuning parameter lambda. Nobody knows what lambda is, so the people use cross-validation to find it in lasso, right? Or any kind of penalized regression. So the idea here is similar. They call it alpha instead of lambda. So they use this cost complexity. And for every possible split, so imagine that here's a mini tree. This could be part of a bigger tree somewhere else. So we're going to consider whether we should split this tree. How strong is this link? Okay. Well, then we compare the value of R alpha t for this tree versus after it's cut. After it's cut, it's just a node, right? So if let me erase this. Okay, so at this node, the error rate is 0.42. After we split, the error rate here is 0.06 and the error rate is 0.016. So it's pretty good split, right? So we're going to compare if we keep this as a tree, and this value is this plus 2 alpha because this tree has 2 terminal nodes, right? And that is 0.22 plus 2 alpha. If we now consider what happens if we cut it. If we cut it, we only have this, which means that the number of terminals is 1, just alpha times 1. And this is 0.42 because it's 0.42, right? So at the end of the day, we will have 2 expressions. We have this and this. There is a value of alpha where it makes no difference whether you cut or not. Right? Just solve for alpha as an equation, right? So after we solve for alpha, the alpha turns out to be 0.01. Then we put a strength of that link at 0.01 on that for that link. So now, if I have a big tree, right? Then I may have an alpha equals to 0.51. This alpha equals to 0.45. This if you cut here, this if you cut here. If you cut here, maybe alpha is 0.32. If you cut here, alpha equals to 0.21. So now every split has an alpha value. Okay. And now if you tell me what alpha to use, I will know where to cut. If you say, I want alpha to be 0.25. Suppose you say, I just talked to God on the phone and God says the right alpha is 0.25. So I start searching and I cut everything that is smaller than 0.25. So then I will cut this off. Right? If you tell me, oh, this is 0.35, then I will only have this tree. I'll cut off that one. Yes, it always decreases. Yeah, that's a theorem. Okay, it's monotonic. Yeah, otherwise it's a bit difficult, right? So now we have a nested sequence of models. Each of them is indexed with an alpha. We didn't know which is the right alpha. So we have alpha starting from 0.21, this one, and then 0.32, and then 0.05, 0.45, and then 0.5, right? We have to choose one of them. Use cross-validation. So 10-fold cross-validation, you take the data, randomly split into 10 parts, take out one part as a test sample, take the 90%, 9 parts, grow this huge sequence of trees, all right? And then for one of these, each of these candidate alphas, you prune this cross-validation tree at that alpha. Now you put your test sample into that pruned tree in cross-validation to get an error estimate of accuracy. Do it 10 times, average the accuracy, right? And then you can estimate the cross-validation estimate of the accuracy of each of these trees in the main tree. And then you choose the subtree with the smallest estimate of cross-validation error. Okay. So I think I have a picture here. So these are just words. It's like this, right? So I have my main tree using all 100% of my data. Oops. Okay, and I have those sequence of alphas. I just don't know which alpha to use. So I now go into cross-validation. And the beauty of this is that, you see, these trees are purposely drawn in cross-validation. They don't look the same as the main tree. So it's very hard to map back what you know in cross-validation. What you do know a lot of in cross-validation because you leave out some data. You do know what is the best subtree in each of these cross-validation trees, but they don't look anywhere like, they may not look anywhere like the main tree. So, you know, they may be, you know, gangly on one side, they may be balanced and so forth. So it's very hard to use the topology of the trees to, even though you know, what is the best tree in cross-validation, it's very hard to map it back. So the mapping here is through alpha, right? So it's like those of you who have used lasso, if you know what is lambda, you don't have to use cross-validation to tune to find lambda. Just apply it and you have a lasso model, right? But you don't know lambda. Here, the lambda is our alpha. Isn't this a neat thing? I think it's beautiful. And it's beautiful. Otherwise, how are we going to prune this tree? So you know that you can keep growing, right? You know that somehow that big tree is too big. You need to cut it back. Even the question of how to cut it back is it's a problem by itself. They kill two birds with one stone using alpha. They use alpha to cut back the tree. Then they use alpha to map from cross-validation back to the tree. Isn't that great? That is a fantastic idea, right? You may forget about how to choose a subtree. How to cut the tree is already a big problem, right? So this is not to say that their method of cutting the tree, pruning the tree, is the best method, but it is a good method in the sense that it is driven or it is guided by cross-validation, right? So, I mean, it may be cutting a bit too aggressively, like the first cut may not be here at the bottom, may not be here, it may be here. So the first cut, you may drop a whole bunch. If you think of this as grapes, you can just drop a whole bunch. So it's not limited to cutting a pair at a time. Sometimes you can cut a whole branch of trees, right? So, okay. Well, I think I'm sort of almost on time. So let's see. So I have all this technical stuff if you want to read it. Then, okay, maybe I'll stop here today and then we'll continue next Monday. All right? Okay, thanks for coming.